Good morning, one and all. I am Dr. Ramya Swetha, Assistant Professor, Department of Civil Engineering from Institute of Aeronautical Engineering. Today, our topic is slope deflection method. So, in analysis of this is the one of the important method which we are going to understand. So, this module, slope deflection and moment distribution method. In this particular lecture, we are discussing about the slope deflection method. So in this introduction to slope deflection lecture, before going to this lecture, what are the various concepts what are involved in this particular module are introduction about the slope deflection and also how we are derive the slope deflection equations, and what are the various applications under various conditions of the beams, as well as what are the various conditions and load conditions in terms of, and different kinds of load conditions we know those are point loads, uniformly distributed load, uniformly varying loads. So different kinds of load with settlement of supports. So in this particular chapter, so application to continuous beam with and without settlement of supports, and analysis of single bay, single story, portal frame, including side sway. So these are the various topics which we are going to cover in this particular under the method of slope deflection method. And move on to the introduction to moment distribution method. How we are applying this moment distribution method, what are the parameters involved in this distribution method, and in continuous beam with and without settlement of supports, and also we are going to analyze single bay, single story, portal frames, including side sway. So these are the various concepts which we are going to cover in this module. So in this lecture, what we understand this slope deflection method is a classical method which we used in structural analysis to determine the movements and also the deflection in various structural elements. So in these movements and deflections we are going to understand in various types of structural elements are involved. Those are beams as well as frames. So it is particularly useful for analyzing the statically indeterminate structure. We know the difference from our previous topics, what is meant by determinate and indeterminate structures. Determinate and indeterminate structures. So indeterminate, the equilibrium equations are enough to understand the given problem. And in indeterminate, for know about the unknown things which are involved in that particular element. So those equilibrium equations are not enough. We require some additional parameters. Such type of structures at the time of the structural analysis, we know that is nothing but the indeterminate structures. So whenever those equilibrium equations are enough to know about the unknown things, that is known as determinate structure. So in this, whenever in this particularly for analyzing these indeterminate, statically indeterminate structures. So in statically indeterminate structure, the structures with more unknowns, those reactions as well as internal forces, then equilibrium equations. And it requires compactability conditions and deformed analysis. In this, it requires compactability equations and also these deformation analysis. In these, we need some key parameter for better understanding about the analyzing about the structure. So here the slope, theta, deflection are there. So in this slope theta, it is denoted with theta and the angular rotation of a member at a joint. So at a joint, the angular rotation is nothing but the theta. Angular rotation. This deflection is nothing but the vertical or horizontal displacement of a point in that particular structure. So in here we have some assumptions. Using these slope deflection methods, we follow some assumptions. Those are: members are prismatic, uniform cross section, material is linearly elastic. It means it follows Hooke's law. Deformations are small. These are the assumptions which we are consider for this slope deflection method. Now, in this, the basic principle which involved in this slope deflection method is nothing but the force deformation relationships and equilibrium conditions. These are the terminology which we remember, that is nothing but the force deformation, that is nothing but the force displacement, deformation relationships, and also these equilibrium conditions. So this method uses the relationship between movements, slopes and deflections to derive the equations for know about the unknowns. So it is a indeterminate structure. And it requires few more equations for know about the unknowns which are involved in the element. So it combines the force deformation relationships and also the equilibrium conditions. So it gives the relationship between movements, slopes and deflections. This is the basic principle which is involved in this slope deflection method. So this is the basic principle which is involved. So here for any member, what we consider for any member AB of a length of L and its flexural rigidity, it is important. The flexural rigidity of the each and every member element which are involved in this slope deflection method, it plays a role for identifying the various movements and calculate and slopes and what are the various parameters which are involved in that particular element. So in this flexural rigidity A and subjected to uniformly distributed or point load, it depends upon the type of load. The things are type of member. It means supports. So whether it is hinged support or whether it is roller support or whether it is fixed one. So like this, and one end have different kind of support. Those two are any intermediate or continuous beams, like that we are going to understand these type of beams. Whether it is simply supported beam, cantilever or continuous like this, and type of support. After that, and which type of member, and also next that's the type of load. What kind of loading conditions are there? These are also various parameters which are going to identify these slope deflection equations. So here in this, for a member of, it has a length L consists and flexural rigidity EI and subjected to uniformly distributed load point load. These are the member end moment equations. That is nothing but these final end movements, those are involved with these slopes and this flexural rigidity, length of the member. These are all the parameters which are involved for the getting this end movement. So these are all the parameters. So these member end movements 2EI by L 2 theta A plus theta B minus 3 delta by L plus fixed end moment AB. So this is nothing but the value fixed end moment. It will come from the what kind of element it is and what kind of load are there. These are the parameters which are involved in this. From this is for A to B. Now B to A also. So B to A is equal to 2EI by L theta A plus 2 theta B minus 3 delta by L plus fixed end movement for B to A. So here movement AB, movement at A due to end conditions and load. This movement which is depends upon the end condition as well as the loading condition. And this movement at B. These theta A, theta B are the slopes at A and B respectively. This delta is nothing but the displacement. So relative displacement of A with respect to B. So this is the displacement which we are going to consider. These MAB fixed one and MBA fixed one are the fixed end moments due to the applied load. We are going to calculate them separately. These are the slope deflection equations. It depends upon the load and end conditions of that particular movement, fixed end moments which are involved. So based on that we are getting these member end movements. Now these fixed end moments for uniformly distributed load, W overall the span is L means that is equal to WL square by 12. From B to A that is also WL square by 12. Coming to these for a point load P at a distance A from and B from B. So here the fixed end moment for this AB is equal to PB square by A and L square. Here P is represents the load. And from fixed end moment from B to A is equal to P A square B by L square. Here A is equal to B means that is equal to P and or otherwise L is equal to A plus B. These are the various conditions we are going to. L is equal to here if A is equal to B means L is equal to 2A. Like that we may understand the various scenarios which are involved for this fixed end movement based on the loading conditions and also what kind of support it is there. So what are the various steps involved for this slope deflection method? So determine the fixed end moment, write the slope deflection equations, apply the joint equilibrium. These are the steps which are involved. Solve for unknowns, calculate the member movements, draw shear force bending moment diagrams. These are the various steps involved in the slope deflection method. First one, determine the fixed end moments. These fixed end moments are going to calculate separately based on the type of the fixed type of the end, what kind of support it is there and what kind of loading system is there. What are the different loading conditions are available. Based on that, we are going to calculate these fixed end moment for each member based on the loading. Write slope deflection equations. Already we understand. Based on that, we are going to write these slope deflection equations using the slopes and displacements. After that, at a joint, use equilibrium conditions to ensure that the sum of the moments at the joint is 0. That is equal to sigma m is equal to 0. Solve unknowns. What are the various unknowns involved in this? Solve the resulting simulations, simultaneous equations for the unknown slopes and deflections, and calculate those members. Substitute the values, these theta and delta, back into the slope deflection equations to find the moments at each end of each member, and based according to the draw shear force and bending moment diagrams using the calculated moments, and construct the shear force and bending moment diagrams for the structure. So these are the advantages of the slope deflection method. So here, suitable for both beams and frames, handle both sway and non-sway frames effectively, provide a clear understanding of the moment distribution in members. These are the various advantages we are going to understand from using this slope deflection method. For know about the unknowns and draw about the shear force and bending moment diagrams. And we are going to use this method for analyzing the indeterminate structures as one of the method. So it is suitable for both the beams and frames, handle both sway and non-sway frames effectively, provide a clear understanding of the moment distribution in member. We are going to understand the particular, whenever the moment distribution in members, we are going to understand very clearly. These are the advantages which are involved in this moment distribution method. In this, limitations becomes it's some clumsiness, some repetitions, and some understanding about whenever we choose for large and complex structures. And it requires assumptions. So already we discussed some of the assumptions in previous slides. The slope deflection method requires the assumptions. So these are the assumptions what we consider in this. Material is linearly elastic and its prismatic deformations are very small. These are the effective limitations for this slope deflection methods. All the time, in all loading conditions, all supportive, what kind of end supports are there, they are not negligible. So also in that particular scenarios, this is going to be limited. And for modern methods, we have few modern methods. This is one of the traditional. Already we discussed it is a classical method. So it is a traditional one. Few more models like matrix method or finite element analysis are computationally more efficient for larger systems compared to this slope deflection method. These are the limitations what we understand as we consider as a major assumptions, major limitations which we are consider for this slope deflection method along with their advantages. So these are the limitations what we understand for this slope deflection methods. We are going to apply according to the advantages and limitations. Based on all the advantages and limitations, this slope deflection method is applicable This slope deflection method is applicable for, we are going to choose analysis of continuous beams and rigid frames, determining the movements and the deflections in statically indeterminate structures, design and evaluation of structural elements under combined loads. These are the some of the applications where we choose the slope deflection method. These are the some of the applications. And how we are understanding these continuous beams and frames without joint translation. So a continuous beam, it is a statically indeterminate and must satisfy the geometric conditions. Those are slope deflection as well as the slope. So a continuous beam, it is a statically indeterminate structure. So we are choose this slope deflection method for this condition, because slope deflection method is used for analyzing the statically indeterminate structure. So here the geometric conditions are deflection and slope. So the slope deflection method ensures geometric conditions are satisfied first, followed by the equilibrium at geometries. So the static equilibrium, this force and moment balance at a joint B, for example, moment with respect to BA plus moment with respect to BC is equal to 0. This provides one equilibrium equation for solving unknowns. So this is the one of the method we are going to consider in this, using these determining the end moments and reactions of the beam, which is shown in figure. So here both ends are fixed and this one is the roller support. So A, B, C, this is the continuous beam. In this, till from A to B, the loading condition is different, that is 65 kilonewton per meter. And from B to C, it is 35 kilonewton per meter. From each has the same length from A to B and B to C, that is equal to 4 meters. So here, and also the flexural rigidity EI is equal to constant throughout the element. In some of the cases, it is also may vary. EI, 2EI, EI, 3EI, 2EI, 4EI, like the different combination we may observe for AB as well as BC. Here, this is constant, this is similar. Now, draw the shear force and the bending moment diagrams for these conditions. So, this is the given data. According to this, according to the figure, we understand. First, find out the fixed end moments. These fixed end moments. So, minus WL square by 12. This is the formula we choose. So, that gives the fixed end moments here. So, here the different load conditions are there for A to B and B to C. We observed according to that we are getting the fixed end moment values. So after that, the slope equations, we are going to find out the equations, slope equation based on the equilibrium condition. We entered all the equations. Finally, we'll get the joint equilibrium condition based on the steps involved in this. Finally, we'll get these equations like this. These are the shear force and bending moment diagrams which we follow for this given condition. We are going to find the moment as well as the shear force. Final, this like this we are going to understand. In next classes we will understand the problems more efficiently. We will see in our next class. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.